Okay, so we're going to continue talking about series today. We're going to look at the divergence test, which is a big deal, in just a second. But before that, I thought we'd review and look at some stickier or trickier issues, if there are any, with geometric series. I think there's one. I don't know if it's going to come up on these first two questions, but an important thing to realize about series in general, not just geometric series, but if you have some rule, which for most of our series, unfortunately, we aren't going to have such a rule unless we look at some reading from Euler and stuff this year from some famous mathematicians. But all the rules that you need to know for the AP exam, most of them don't have an actual value that the thing converges to if you have it. Geometric series are really special in that respect. But whether or not they have a rule for determining the actual convergent value, if they do, all series, be they geometric or not, these guys are obviously geometric, but whether they're geometric or not, the convergence, divergence of that series can't be affected by like a finite number of stuff at the beginning. Yeah? What's weird about that first series there? It starts at 4 instead of 0. The way we've been learning geometric series so far, it's supposed to start with 0. And if it doesn't, you have to like shift it so that it does start with 0. And that's what we're going to look at today, is some trickier shifting issues. We'll follow up on that tomorrow. So this has to be shifted several terms backwards. This isn't asking us, in other words, to add up all the terms from 1 to infinity, but just those from 4 to infinity. So how do you deal with that? Well, let's remember that convergence, divergence isn't going to be affected by just like having a few less things instead of 0 to infinity, only 4 to infinity. So just pretend that it's 0, find the convergent value if there is one, and then subtract the other stuff. That's the whole idea, right? So you don't even have to do anything fancy on this problem. It's geometric because it matches the form where the power of n is here. There's other alternative ways of doing geometric where you use powers of n minus 1. I'll be talking about that today and tomorrow as well. But we're sticking with our book's approach just because it's our book. It's just as good as any other approach. Okay, so the first, if it converges, or does this converge or diverge? You guys tell me first. It converges because r is 1/2, which is less than 1. Sweet, exactly, between 0 and 1. Okay, so we know this guy's convergent with r being 1/2, and it's a geometric series. So we'll just pretend that it's 0 to infinity instead of 4 to infinity and find its value. What does it converge to? In fact, it's convergent to what? 2. What's the first term? You put a or a sub 1 up on top, which is 1 over 1 minus r. So it's going to be 1 over 1/2, which is 2. So this guy converges to 2 if you're adding the terms up from 0 to infinity. But you guys said I needed to subtract something if I'm only going from 4 to infinity. So that series, the series from 0 to infinity goes to 2. We're going to have to take 2 and subtract terms 1, 2, 3, and 4.
Doesn't that include 4 though? Doesn't that include 4 though? N equals 4.
What's weird about my notation here, we're going to have to be real careful about our subscripts. That's what I'm starting to talk about today. So Gabe's saying, doesn't that include 4 though?
Yeah, but
I need to subtract 4 things though.
You're doing
N equals 0.
0, 1, 2, 3.
The way it's named though, shouldn't I have said it like that? Yeah. And that's because just of a naming choice. The way our geometric series is set up in our book is you go from 0 to infinity, and it's r to the n. In other books, like the other one I'm pulling examples out of, instead of being like that, it goes from 1 to infinity, and it's r to the n minus 1. N minus 1, that's counterintuitive to a lot of people. So, nice. So what's this going to be for us? It's going to be 2 minus, well, what's the first term? When we put in 0, it's going to be 1. When we put in 1, it's going to be 1/2. When we put in 2, it's going to be 1/4. When we put in 3, it's going to be 1/8. So we got to go 2 minus that junk. That's 2 minus what? 12 plus 3 is 15. So it's 2 minus 15 eighths. Hey! That converges to 1/8. Sorry, my writing got a little sideways there, but you guys can. Okay, let's look at our second one then. Do we have any issues with this, or can we just go straight into geometric series? We got to move at 1. Now you can do index shifts. I'm going to show you the third example here is going to have an index shift in it. I'm going to ask you guys to make sure that it's right. It's kind of a little homework problem. But let's just do it the same way, shall we? Let's just pretend that's 0 to infinity and go, well, if it was 0 to infinity, what would it converge to? S for, so let's say 0 to infinity, inventing a notation here. 0 to infinity would converge to S equals 3 over 1 minus 3/4. So we got smart Alex here. We're like, well, that's this. So that's 12. Nice. So this guy's going to go to 12. And how many terms are we going to have to subtract? Just the first one. So subtract just the first one, and there you go. I'll look at something real quick. So what should I be subtracting?
3.
Yep. So that guy's going to converge to 9. Cool? All right, let's look at one that's a little bit tougher. Let's see. So once we get further into series, I mean, you're going to have a whole bunch of different techniques that you can use on series. They don't have to be geometric or telescoping. Do another telescoping one tomorrow, just to review it. They can be all kinds of different things. So first, looking at this problem, you might be like, well, that doesn't look geometric at all. It's got to end in more than one spot, right? But sometimes you just want to play with your algebra and see what happens. Help me play. So I'm going to try to make it look like the form that we know. So we got ends in 2 spots. That's not good. Can't you write this? Isn't that the same? So we need to keep simplifying that until we can get it into the form. So you can see that the ends are starting to emerge here. So I think the next step is pretty natural. My students thought it was. So you get this. 2 squared is 4. And then on the bottom, we're going to have, because of the negative power here, 3 to the n minus 1 power. So now that's really starting to look a lot more like a geometric series. The only problem is we have n minus 1 on the bottom and n on top. So there's a variety of ways you could handle that. In my class, one of the students chose to handle it like this. They said, well, let's just turn this into an n minus 1 power and say 4 to the n minus 1. Leave that on the bottom as n minus 1. That way they'll both be n minus 1. But you can't, of course, just do that arbitrarily. How is this power going to add up to n? Well, if you go like this, they add up, because here you have powers that add, right? So 1 plus n minus 1 is n. So that's the way you do it. So that's the way my class decided to do it. So they wrote it as this, and we'll continue there in a second. So now you've got that blue 4. I guess I'll make it blue. So here's the blue 4. So we usually put that term in front, right? And now this is all 4/3 to the n minus 1 power. It's also, of course, possible on this problem to have taken this guy and instead of matching it to the bottom, match it to the top. So you could have 4 to the n, and then on bottom you could go 3 to the n, but that's really just 3 to the n times 3 to the negative 1 if you use your addition power exponent rule. So that is that, but now we want to write this as 4/3 to the n. How would we compensate? Well, 3 to the negative 1 would be the same thing as 3 up there. And I think we'd get the same thing that way. So this would be another way to handle that same problem. We're going to have to switch and do a little more work here in a second. So let's see that. So, as we were saying, we're going to go with this rearrangement. So now, how can I write it?
Well, we have to do 4 times.
And this is 4/3.
But you need your 4 times.
But I need the other 4. Where should I put it, Kyle?
Just do it on the outside.
Probably in front is best because now it's starting to look like our geometric form. Yeah? So what's the only problem with this form? It's starting at 1. Now if you look at like my Stewart textbook, like the calculus book that I used in high school and college, this would be the form of geometric series. So we'd be done. We'd write equals. Straight here you can go equals A over 1 minus R, just like we've been doing. Why?
Because you have the n minus 1.
Our form has been going not from 1 to infinity, but from 0 to infinity. But the n minus 1 does kind of compensate. This is known as an index shift. So is this really equal to what we've been doing? Well, yeah. I want you to really think about why, though. Why is this really equal to this? Index shift from going to 1 to 0 has extra or less terms in it. Think about it like that. We just did that a second ago. Extra or less as you go from here to here. Here to here. This one has less than this one. This one has 1 more than that one had. This one has what again? Say it one more time. 1 more than that one had. So if this index was n minus 1 power, that index is 1 more. What's 1 more than n minus 1? N. This is kind of weird, but it makes sense.
Does it work?
As long as you understand that this has less terms in it than this by 1 extra term. This has this one has 1 extra term, and you're real clear about which one has more, then you'll realize going from 1 to 0 is a shift with more, so I've got to make this be more. Okay? If you're going this way, you're going from more to less, so you've got to take away in your exponent. And those are exactly the same thing.
Does it work if that was like 2?
Yeah, you can still shift, except sometimes you're going to have to do that subtraction thing like we did a second ago, right?
Well, like if it was n equals 1 down there and then n minus 2 up top, would that be the exact same thing?
N equals...
Like on the top one. N equals 2, and then it was to the power of n minus 2. Would that also work?
Yeah.
Okay.
Yeah, it would. Good question, Katie. Yeah. So index shifts we're going to start to see here and there. Those are some of the harder level AP questions, I think, but very good to deal with, especially for advanced engineering. Okay, so that guy is going to converge to, the answer is yes here. So we're going to get 4 over...
Wait, but it's more than 1. 4/3.
Oh. All poop. Should I even have done this? No, we'd have to say that that diverges. These are equal though. These guys both diverge. I think I wrote my problem down wrong. Let's see. Just a real quick check. different than the one in the book, but ours diverges, okay? Let's look at one more thing. Okay, so the last thing we're going to look at today, guys, is called the divergence test. It's very easy to use the divergence test. It's very easy to use logic wrong and use it the wrong way, though. The mechanics of the tool are very simple, but a lot of people use it incorrectly. So I'm going to try to make it real clear. So first of all, there's this fact that emerges about sequences and series and how they relate to one another. There's a nice proof of it. It's a real easy little proof, which hopefully you guys read. If you didn't, I'd read that this evening. So it says if the series, and where the index starts really doesn't matter too much, whether you start at 1 or 0, wherever you're starting. That's why I left them off, okay? So if the series of a sub n converges, and you know that that's true, then what else do you know? If adding the terms up, if the limit of partial sums converges, and you figured that out using whatever way, geometric series telescoping or something else we haven't learned yet, if that's true, then you also know something about the sequence. This I think should be pretty intuitive. If the series converges, that's a powerful thing. If that converges, then the sequence is also going to have to have been something that was converging all along. So there's a nice little proof of this that I'd like you guys to look at in the book. It's not hard. It's just using notation basically to figure it out. But anyway, that's a way to look at sequences. Well, sequences aren't that hard to figure out in the first place. It's series that involve a little more work. That's why we're going to spend a whole bunch more of our time this year studying them. So can you somehow turn that around into something useful, not about sequences, but about series? The answer is yes, using logic. So going back to your geometry days, if you have a statement, an if-then statement, in other words, a conditional statement, anything like that, it says if-then, there's the inverse, the converse, and the contrapositive. Only one of those three things has the same truth value as the original. Contrapositive is the one. So the contrapositive of this statement is also true if it's true, and it's a proven statement. So how do I do the contrapositive of this statement? Because that's the divergence test. You don't need to remember this. You need to remember it's contrapositive. So if the limit of the sequence is not 0, very nice, you negate the conclusion,
Then it diverges.
then the opposite of converges is diverges. So then the series diverges. That's not a hard statement to understand. It's not a hard statement to use. It is a hard statement to use correctly. People use it incorrectly all the time. So we've got 3 series here that we want to evaluate using the divergence test. Notice its name. It says it's a what kind of test?
Divergence.
It's the divergence test. Does that mean you can use it to show that things converge? And that's what people try to do with it. All it tells you is, hey, I suspect this thing might diverge. Can I apply a quick check? And it's a quick check. Quick, easy check. That's how you want to think about it. It's not a way to figure out that something does converge. So, what do you guys think? If we add up powers of 2, this is basically, let's just think about what this is doing, right? It's 2 to the 0, which is 1 plus 2 plus
4 plus 8.
Does that look like it's going to converge? Clearly not. So it doesn't look like it's going to converge, but it actually is geometric, so we could use our geometric rules on it. Ours, in fact, doesn't it match geometric perfectly? So by geometric series, in fact, we have another tool that says it diverges because R is bigger than 1. But you can also use the divergence test. Just take the limit of the what again? The limit of the sequence. Make sure you're real clear about that. You're using the sequence to tell you something about the series. So if I take the limit as n approaches infinity of the sequence, notice there's no sum in there. I'm just looking at the sequence. What does that go to? That's clearly infinity, right? We don't need to even talk about it. And since that's clearly infinity, it's clearly not equal to 0. So we'd write this. We'd say, therefore, by the divergence test, and you'd want to write it out if you had more room, if you're on the AP exam or something. Therefore, by the divergence test, the series of 2n diverges. Okay? You could have also talked about how this is geometric and it diverges by geometric rules. Be fine too. What do you guys think about that second one? We can start writing out some terms. I'm not going to this time though. You guys get the idea. The limit of its sequence is this. Now I know it's factorials, and we still don't have a lot of experience with factorials. But what order of magnitude is the growth on the top? N factorial. What's the order of magnitude growth on the bottom? No, 2n factorial means this.
2 times.
It's just n factorial growth then multiplied by 2, right? That's what that said. It said n factorial growth doubled. Doubling factorial growth doesn't affect it very much. The order of magnitude is still factorial, n factorial. So this is an order of magnitude limit. What's its answer?
1/2.
Because the orders are equal, so you do the ratio of their coefficients, right? Whether it's factorial, exponential, power, it's the same thing. You just haven't seen one like that before. So what do I conclude? That's not 0, so this guy diverges. And I want to write that out as by the divergence test, okay? What do you guys think about this one? If I look at this third limit, Derek, you said the limit as n approaches infinity of that thing is?
0.
Really, 0? It's classic. This is all known as the harmonic series. We're going to look at that more later this week. Wednesday, Thursday, and Monday. So, does that mean I conclude this guy converges?
No. You just know it doesn't.
I just know that it doesn't diverge by this rule of thumb test thing, okay? I cannot say it converges. In fact, this is the classic example, the most famous divergence series. This guy diverges, even though you can't tell it with a divergence test, okay?
So this is just to tell.
So we'd say, what could we say here then?
This does not diverge.
The divergence test is inconclusive. Okay? What the divergence test does basically in math, here's the way you want to think about it. It checks to see if the limit of the sequence, if that sequence itself is decreasing fast enough. Is that sequence decreasing fast enough so that when you start adding stuff in that sequence together, you'll get down to something finite? And if that sequence doesn't limit to 0, then it's not decreasing fast enough within itself, so that when you add up the partial sums, you get something finite. That's really what the divergence test does, kind of on a little bit higher level, a little more abstract level. Okay? That's all you guys need, I think, for this assignment. So I'll see you next.
Good job.